Okay, so this afternoon we have a presentation from the pronunciation modeling of Mandarin team. Pascale.
Is it possible to turn off the light as
No doubt it's possible. That doesn't mean we know how to do it.
because that's really hard.
Random light going out and coming back on.
Who's president? He was a great character. He was in his t-shirt, his jeans. That's what his name was.
Perfect.
No. Do you want to turn it back on?
Whatever you want. Charles loves being in the dark.
Let's turn it back on.
You said it's perfect.
Okay, let's turn it back on.
Pascale, we can't see. It's really hard to see with the lights on.
You want to see with the lights on?
No, it's hard to see what's on the screen with the lights on.
So you prefer this way?
It's a binary choice, yeah.
I feel like I'm being filmed or something. I am being filmed.
All right, start.
First start experience. Okay. Well, welcome, ladies and gentlemen, to our presentation of our group's work over the summer on pronunciation modeling of Mandarin casual speech. I'm sure that you will. Let me introduce the group members. Hello, where are you? I'm Pascale Fung. I'm not wearing a name tag because I lost it, so you should remember my name. Pascale. Bill is over there. Zheng, Professor Zheng, Tsinghua University. Terri from DOD. Okay, yeah. Liu Yi from UST, University of Science and Technology. Zhanjiang from Tsinghua University as well. Veera Venkatramani from Veera? I can see you. Okay, and Umar Ruhi from there as well. Do you guys want to sit over here? No. Okay, so we'll start our presentation. I'm sure you will have a lot of questions, and I would like to ask you to refrain from asking long questions until our discussion session afterwards. Let me briefly describe our project objectives first. What we wanted to achieve when we started this workshop was to do the following. Number one, we wanted to develop a Chinese annotated spontaneous speech corpus. And then we want to build a baseline Mandarin system on broadcast news. And then we wanted to further select and model generalized initial finals. I will explain what they are later on. And also we wanted to do acoustic modeling for generalized initial finals and initial final units in Mandarin speech. And we want to apply the pronunciation lexicon using this generalized initial finals to recognition. Another objective was to find predictive features for pronunciation changes directly from data. And of course, we wanted to try applying the models that are trained on this CAS database that we developed to broadcast news and to see whether we can use such information across domain. Let me first give you an overview of this CAS database. This was developed. This was radio station. This was data collected by Tsinghua University radio station, consisting of lectures and seminars delivered in lecture halls and classrooms and so on and so forth. There were 3 hours of those data that was annotated by the Chinese Academy of Social Sciences, CAS as well. And this is the format of annotation. Let me just give you an example. There are actually 5-tier, there is a 5-tier annotation. We start with the canonical or the original, well, we start with the acoustics. right? People listen to them and transcribe into the canonical Chinese character string. In this case, this example, it is 我们多认识点人. Let's know more people. Okay, and then the second level will be the pinyin base form. Pinyins are the phonetic transcriptions of Chinese characters that you can find from dictionaries. This is base form, dictionary form of these characters according to the word context. So here, for example, we have 我们多认识点人 according to dictionary form. And the CAS pinyins are a little slightly different from dictionary form in that they allow the linguists at the Academy of Social Sciences allow multiple canonical forms, such as here. Because in this case, the words are actually pronounced, instead of saying 我们多认识点人, it was pronounced as 我们多认识点人. There was a retroflex after the 点. It became 点. And this is a common occurrence in Mandarin speech, especially in the north. And this, therefore, CAS pinyin transcribed 点 into 点. And then the CAS generalized initial finals transcribed then according to CAS pinyin, according to what they hear, actually not according to CAS pinyin, it's actually directly to what they hear from the acoustic waveform, the actual semi-syllable or the initial finals. And then because they are initial finals, they hear that that's different from the canonical set of initial finals, such as here. So if it was in canonical form, you would transcribe 我们多认识点人 into the following initial finals. 乌, m, an, tuo, so on and so forth, right? Initial finals. But what they hear, this is what they actually hear. 我, they heard 我, but the n was missing in 门. So they didn't transcribe that, so there was a deletion. And here in tuo, it was actually pronounced voiced in casual speech. So they put the sound change here, underscore v. Okay, and then here, 多认识, shi, again, in canonical form, is supposed to be shi. Okay, and then when they listened to the casual speech, they heard the voice form of sh, and then there was a missing final. Okay, it wasn't there. And then the dier, and then was voiced again in the actual sound they hear. And then there is this retroflex that's not in the canonical dictionary form. Okay. So this is first tier, second, 5-tier description of this sentence. And then there's a last tier transcription in the CAS corpus, which is miscellaneous, which consists of various kind of noise and murmur and all that. For example, here, there's a time indication of, between here and here, there's some background noise. Okay? This is basically what we get from the CAS corpus. All right? And the third level CAS GIF level is actually it's transcribed according to Sampa C convention. All right? And these are the various noises at the miscellaneous level, and we actually collect all this data together for garbage modeling in our acoustic modeling stage. Okay, these are some of the statistics of various phonemes in Chinese. Again, here. So let me introduce the generalized initial final. This is a definition we introduced at this, according to CAS corpus at this workshop, which is basically an extension of the canonical initial final set in Chinese phonetics. For example, in this example, the canonical form of zi, originally it should be this initial. And when there's a sound change, when it's voiced, then there's underscore v, and this is a retroflex, zhi becomes zhi, and then voiced and retroflex. Okay, so this kind of these three symbols, okay, they're not in the standard Chinese initial final set. We include them in extended generalized generalized initial final set. Right? So of course there are more than these three gifts. Well, this is what the linguists claim to have found in the transcription of the CAST database. They found that their initials were changed by initials, the original initials, canonical initials, changed around 27%, finals changed at 12%. We found otherwise in our experiments, but this is what the linguists claim after they did transcription. All right, let me give you some overview. Maybe we can come here. Oh, we'll come here later. This is, we have basically three branches of the group that carry out three types of research. The first one is that, I will go through this presentation later, is that we try to model GIFs directly from the CAST database. And because there's not much samples in there, we were just trying everything we could to bring up the accuracy on GIF modeling, and hopefully we can apply that to a different corpus later. Another group, Professor Zheng's group, basically also worked on CAST database and worked on GIF and IF modeling. They use a slightly different approach, and he and Sun Zhanjiang will present their work to you later on. And Bill and Veera and Terri and their group basically use a decision tree approach by first using some rules they derive from the CAST database and applying it to broadcast news database, and they will present their work later on. So I would like to leave this is the first roadmap of the first group of work we're going to present, so I'm going to leave it up here. Okay. Before we go into that, I would like to invite Umar to talk about his work on flexible alignment tool.
Okay, basically what I've been working throughout the workshop has been writing some tools which can help us during doing the alignment. Our purpose was to have a tool which would do alignment for different symbol sets. So no matter what symbol set you want the alignment for, we would have something for that. So originally, we can do this for the sample C symbols, we can do this for the initial finals, we can do this for the triphones, whatever you want. So that is the original purpose of writing this tool. Once you get the cost transducer, you can use that cost transducer with the FSM toolkit in order to align your utterances for the base form and the surface form. So that is what I've been doing. And once you hear from the other group members, you can sort of know how they use the tool throughout the workshop. So this is a simple example of okay, this is a simple example of alignment within a base form and a surface form, and it tells you why the string at a distance is inadequate. So given this base form and this surface form, what is likely to have happened here is that EI was heard as AI, right here. I was inserted in the surface form, right there. Z was deleted, and AI was heard as an A. So this is why the string at a distance is inadequate, otherwise it would align perfectly because the string lengths in this case are the same. So we wanted a cost transducer which would have different costs between different symbols. The way we do that is with acoustic classes. So this is an example of Mandarin initial final acoustic classes. So you have your classes here, what initials belong to that class, have a class of finals here, and what finals belong to that class. So depending on what class the initials of the finals belong to, you can have a cost metric between those symbols, or between those initial finals. So as an example here, what I'm going to show you is, let's say the difference between AI and AN finals. Let's say our cost is 3, right there. And the distance between AI and EI is just 1. So AI is more similar to EI than AI is more similar to AN. Going back to the slide, why is this so? Let's take AI and EI first. So AI and EI come together in this class right there. They come together in this class right there, and they're together in this class. So very often they appear together in the same classes, whereas AI and AN only come together in this one class, so they're not that much similar. So there's more cost from AI to AN than there is from AI to EI. One of the purposes of our tool is multiple tier alignment. So you can have your base forms and surface forms in terms of initial finals. We can have our strings in normal characters, in our opinion, and the tool should be able to align any of these tiers with any other tier. So maybe the surface form is on the tier of initial finals, and the base form has another tier. So you want to be able to align those two tiers together. And the flexible alignment tool basically allows you to do that. So that's the basic purpose of that. The aligner can also be extended to do more stuff. So you have your aligner, you have your costs between the different symbols. We can add more rules to that. So you can add some diacritics information. For example, sound changes due to voicing. You can have some insertion and deletion rules. So initials tend to get deleted more easily than finals do. So you can have rules for those. So there's more cost of insertion or deletion depending on what symbols we're inserting. Additional symbols, for example, the garbage model symbols that we just talked about, for example, the breathing, the lengthening, if you want to include those in your matrix, you can add those. And merging rules, for example, when an initial and a final are combined into a single symbol, like U and AI, give you a UAI. So you want there to be no costs when these two align with a UAI. So those sort of rules can be added. One of the things that we're going to do is anybody who's interested in applying this tool to any other languages or any other domains, we're going to make this tool available publicly as open source. And a purpose of writing this tool was that if you want to apply this to other languages, to other domains, it is very possible. So if you have the FSM toolkit, you can use this tool to produce your cause transducer. Okay, and I guess that's it for me.
Now I'm going to introduce the work Liu Yi and I have done together on the GIF and IF pronunciation modeling. First of all, this is what we discovered in the CAS database, that there are not many phone changes manually in the CAS database, meaning one phone, one initial or one final that's actually heard as a different initial and final within the canonical set. There are several reasons that could cause this to happen. Number one, possibly because all the Mandarin data we allow or we collect in CAS database is standard Mandarin. Nobody had any accent. That's on purpose. Secondly was that, another reason that could possibly cause this is that the people pronounce, because Mandarin characters are syllabic, so maybe that leads to fewer changes. And another reason actually our group believes really is the reason is that the linguist transcriptions are a little bit subjective or too detailed for our purpose. They transcribe it according to their research or their linguistic standards, but for recognition, we actually need those phone change transcribed. So that's probably the main reason. However, we have to work with this, and we found that from the database there are more sound changes. Okay, phone changes is when A becomes an E. Sound changes is just when a T becomes a T underscore V, or D becomes a D underscore U. These are called diacritics, and it's just retroflexed or voice or unvoiced variations of a canonical initial final. And also, they don't become another canonical initial final. In other words, T underscore V is not really D in Mandarin. Okay, right. So we found there are more sound changes. So we feel that using GIF models, the generalized IF models, will model this better than just using canonical IFs. However, we also discovered that in the CAS database, there are not many samples for these sound changes. The only one that has a lot of samples is voice. You know, any sound that's changed into voice version of it has a lot of samples. The other artifacts, the other diacritics such as unvoiced or anything else, we don't find many samples. So we want to model those, but what can we do? So we want to try our best to model these data, model these GIFs in the sparse CAS database. And we want to see that after we try different methods, if that brings some improvement in the CAS database, perhaps we can use the same methods to another database, such as Broadcast News or some other bigger database. Okay. The first method we tried is the probabilistic GIF models. We reasoned that GIF models model sound changes better than IF models. However, if we add more GIFs into the pronunciation dictionary, we just have more ambiguities. So we incorporate probabilities on these pronunciations. And in fact, indeed, we got better changes. So this is the first thing we did here. So we have two branches here. One part we were trying to improve the GIF models. The other one we worked on IF models for comparison. I mentioned that we use garbage models. All right. Okay, the first thing we did was probabilistic multiple entry lexicon here. Okay.
What does the G stand for?
Generalize. All right. So you can start out with a DTW alignment of base form and surface form, or using Umar's tool to do the flexible alignment, and you get the following probabilities. I'm sorry, this is supposed to be Liu Yi's slide. GIF 1 given GIF 2, GIF given IF, so on and so forth. Okay? So this is the first method we tried. Now I would like to turn over to Liu Yi and talk about the second thing, which was the state-level Gaussian sharing. This, by the way, I should acknowledge that this is similar to the approach Sanjeev and Murad used for the English triphone Gaussian sharing. Liu Yi.
After we try the probability multiple, after we try probability multiple entry lexicon, we then do state level Gaussian sharing in initial final list level for comparison. The basic idea is something like we believe that in Mandarin, if we use state level Gaussian sharing, the phone changes can be added in one model. Also, we think that a more robust modeling of sound change by sharing between base form model and the surface form model. The method of share Gaussian mixture is we give the base form alignment, then we do a decoder, generate the surface form from the CAS corpus, use phoneme decoder. After that, we use DP alignment between the base form transcription and the surface form transcription at the state level. In our experiments, we use Umar's flexible alignments tool, so that in this DP alignment, use Umar's DP alignment, we consider the cost matrix, so it should be more accuracy than traditional method. After that, we use normalized alignment frequency to generate the state variation probability between the base form and the surface form model. Page down. Here I give the example of state level Gaussian sharing. this is the base form. This is base form K, this state number, and this is the variation probability. This is from the surface form. This is the state number. This is another example. We can see that in this level, the state 3 may be connected with another form, state 2, with this probability. Here is the equation of this state level Gaussian share. B means base form states, S means surface form states. This is the probability of Si given Bj. It comes from the count number of C, Si, Bj, and the sigma. We get the summation of this one, of different I. For each Bj, we select the top n list, and then we have this equation. After that, we do normalization and let the summation of lambda equals 1. This is the output distribution. We write this is the weight, this is the PDF. When we add the pronunciation model from here, from lambda, we get the new output distribution P, O given B. We can write in this formula. So add this one to this one, we get this formula. This is lambda K times WJST is the new shared weight value. So it's okay. Okay, this part should be returned to Pascal.
Can we have two of this?
The podium might work too.
Huh? Oh, here. I see. So we tried the state sharing method actually, we only had time to do that for initial final models on the canonical form. We believe that it can be used for GIF and IFs. We also try another method to interpolate between IF and GIF models. As we know, it's the generalized IF models. You really need to transcribe it. You have to listen to it, transcribe it. You cannot derive that from canonical character transcription. So it is time consuming to transcribe these GIFs. So we'll never, even in the future, we'll have more database. We can never transcribe enough of this. We can never have enough label GIFs. So we need to, but however, we know that these GIF models are extensions of IF models. So P underscore V comes from P, B underscore U comes from B, and so on and so forth. So we think that we can bootstrap from a small amount of label utterances containing both GIFs and IFs, and then do a deleted interpolation between these models to get better GIF models. All right. Deleted interpolation, I'm not going to go into the details. It's basically we're going to train the weighting between canonical IF model and the generalized GIF models using EM by chopping up the training database. And we use this on the 3-hour CAS database, which was actually largely inadequate. Okay. We saw that for most of the diacritics, there are only less than 5 samples. How can we build a GIF model with 5 samples? So in these cases, of course, the weighting is will be biased towards the base form model. So in the actual recognition for such cases, they will actually be largely borrowed from the canonical IF model to do recognition. And we also found that the voice diacritics occur most often in the CAS corpus. It's voice diacritics of all kinds of initial and finals. All right. If we have more, we obtain the improvement. This is the last thing we try here, right, on the CAS GIF models, and we got some improvement, and we wonder if we can see more improvement if we have more database. So these are the results. Compare. The baseline was really low. These are syllable accuracies. Okay, the baseline will start out very, very low because there were not enough samples for training, and also it's a very noisy database with a lot of echoes and background noise and so on and so forth. The purpose of our experiments is to see how well, if we can improve this at all with all the different methods. And in fact, we have improved. And at the end, when we use diluted interpolation, on GIF, it still works better than Gaussian, state-level Gaussian sharing on IFs. So what we're going to do actually, is that we're going to do state-level share Gaussian for GIFs as well, and then bring this up even further. And then we're going to do the whole thing on broadcast news or some bigger database.
What is the first and second figure of it?
Correctness and the accuracy of syllable accuracy.
It's correctness and also accuracy.
Yeah.
So correct minus the number of deletions.
I see. Correct. All right.
Yeah. So we had the 6 weeks, and basically the first 3 weeks we spent a lot of time working on cleaning and reconciling various transcriptions, different level of transcriptions of the database. So we had about 3 weeks to do to carry out these experiments and to improve the baseline somewhat. Well, of course, we're still not happy with this final accuracy, but it sort of tells us that these methods can be used when we don't have a lot of GIF transcriptions. So we want to continue to do that in the fall on another database. This is basically what I just said before. Okay, it was suggested also that we compare diluted interpolation with map adaptation between GIF and IF models. Okay, I'm going to turn over to Professor Zheng on their pronunciation modeling work on GIFs and IFs.
Good evening, ladies and gentlemen. Our project at Byrne is to do some experiments to model the sound change and the phone change in the spontaneous speech. In the cast data, because in the cast data there is some sound change, the phone change. How to model it is a problem. Let's see the equation. This is normally for a speech recognizer. The goal is to find such a sequence of canonical initial finals or canonical pinyin here. So we try to find the most likely sequences for such pinyin strings. And just using this equation, we cannot recognize for the GIF or for the GIF strings. So we made some independent assumption here to develop this equation into this one. Here the A is acoustic and K is canonical. Here we call canonical initial or final. And the A is capital A is a strain of A, and capital K is a strain of canonical pinyin, canonical initial finals. So in this equation, we can find the pronunciation modeling part can be divided into two parts. One is this part. It is related to the acoustic model, and this part is related to the pronunciation model part. So we try to do these two parts together to try to improve the overall performance. Here is a roadmap for us to do the experiments. First, we model the initial and the finals, and do the models generalized initial and finals. And then we use do some estimation for pronunciation weights and refine the acoustic models according to the initial final to the GIF mapping. And then we try to integrate the two parts together to get the whole pronunciation model parts. And then at last we apply the language model. The language model is only on the syllable level, not the word level. So this is an overview map for our experiments we have done. So for the acoustical model part, we try to model the IF and GIF with where there is sparse data, there is not sufficient data here. This can be used to stand for this idea. To model this, I think there is some solutions here. One is the straightforward idea is just use canonical models here instead. That is very straight, very simple, but the result is not so good as expected. So another solution is to use a surface form. I use a GIF model here to be an alternative of this part. But we don't think these two forms are good enough for our model of the IF GIF. Because, in the sentence we know that for every canonical initial final, it can be pronounced as a GIF. But the GIF, which is changed from initial final 1 and changed from initial and final 2, we believe that it is different. They are different. They are not the same. So we try to refine the GIF by using two kind of methods. One is to adapt the canonical models to this model. We call it B base form GIF scheme. Another way is to adapt from the surface form models, that is to say the GIF mod to this part. And we call it the surface form GIF scheme. In these two methods, I think the technique we use here is adaptation techniques. And another thing we must do is that we should generate the initial final and to give mapping such transcriptions for use of this adaptation. This is the acoustic model part. And another part is context equivalence class for the pronunciation model part. That is this part. Actually, I think this is the output probability of the surface form given as canonical initial finals. So a straightforward idea is to learn this probability from the cast data directly. But we know that because the cast data don't have enough data for us, it is only 3 hours data, so we cannot sufficiently train this model. But I think that this model is focused on the pinyin or syllable level. The syllable level data space doesn't mean that it is sparse in the initial, final, or GIF level. So we try to split this formula to a lower level, such as this. We call it context-dependent weighting. Here there is we first give this is the output probability of the GIF given the canonical initial final. We can develop this term into these two parts according to its left context. This is the left initial final of this initial final. So these two parts, this part is output probability given the context, the bigram context. And this is, we can see this is similar to the IF transition probability. So these two parts can be easily learned from the cast data, and I think the data is sufficient enough for models such two parts. And here we get the results, experimental results. So we see that this is canonical modeling, and the result is like this. This is correctness and this accuracy, all based on pinyin level. And this is an independent GIF model, and the result is this. We can see that this is lower than this one. That is, the independent GIF model is not so good as independent initial model. But when we go from this part to this part, that is, we add the weight here, we can see that anyway it will go higher. For this is a contact dependent weighting. For this the direct out probability weighting here, we can see all get higher. And another branch is to use a refinement of the acoustic models. We can see that both the surface GIF and the base form GIF, we get higher improvement like this. And when we merge that, integrate the two parts together, it will improve a lot. The syllable error rate will reduce by 6%. And this is the whole part is GIF modeling, and this part is initial modeling, initial final modeling. We can see that this part is better than this part. And when we integrate the syllable n-gram, we can see that this will improve relatively it will improve a lot, and the syllable error rate will reduce by 10% here. Okay, now this Zhanjiang Song.
Okay. Due to the time due to the time is limited, so I only provide one supplementary, detailed supplementary experimental result to the previous slide. Here I give the comparison result between GIF, this is the GIF result, and this is a experiment on S-GIF results. So in each result, we give the experimental result on applying no probability and applying the DOP. It means directly output probability, so the conventional probability, and the new CDW, context dependent weighting. So when we apply these three methods to the GIF site, we can see from the left to right, all is they have some improvement. So for the blue bars, they are the accuracy of sample higher. So here means given a pin lexicon, then we measure the GIF accuracy. And for the red bars, they are given the pin accuracy. So here we take the pin accuracy as the final to evaluate the final performance. So and here is the result on S-GIF. So we can see from the non-probability lexicon to conventional probability lexicon and to new context-dependent weighting, the performance is improved. Have some slightly improved, just as this part. So in the third chart, we compare the GIF. We compare the GIF result with the S-GIF result. So the blue bar means the GIF result, and the red bar means the S-GIF result. So for the baseline for the non-probability lexicon, the S-GIF outperforms GIF, and for the DOP and for the CDW, the result is the same. So this method has some improvement. So here we come to the, I will present some analysis to the previous results. So the first one is GIF modeling is better than IF modeling. The GIF modeling is better than the IF modeling. Here, we think this is just because the GIF set will cover most of the necessary sound changes. But IF modeling cannot cover the necessary sound changes. And IF GIF modeling, here IF GIF modeling means the B GIF and the S GIF. Here is the B GIF and S GIF modeling. So this is better than both IF modeling and the GIF modeling. Here we can say that the IF GIF modeling is a refinement of IF and GIF. So because in the same if we only model the GIF set, there still exists some confusions in the GIF according to different initial and final. So when we use IF and GIF, we can yes. So when we use the use BGIF and SGIF, the sum of the inner confusion of the GIF can be avoided. So the overall performance is improvement is improved. And the third conclusion is the context-dependent weighting is more helpful for sparse data than directly output probability. I think this is just because when we use this kind of weighting, the context, the actual context of the database is taken considered. So this just as we use n-graph language model or something else. So use this kind of weighting, we can better modeling. We can better reflect the probability of the sparse data. And finally, according to this experiment, we can observe that the cross-domain scalable n-gram is useful to this experiment. Here we have 3% absolute improvement and 10% relative improvement to the previous experiment without a language model, a scalable language model. And this conclusion is SGIF outperforms BGIF. Here, because we, according to the previous explanation, we produce the SGIF set from the GIF set, but we produce the BGIF set from the IF HM set. So they are produced from different acoustic models. So when we use SGIF, it will introduce less acoustic differences than the BGIF does. So the last analysis is a multiple entry lexicon is useful for sound change modeling, but the lexicon size should be moderate. Here we had some experimental result to support this conclusion. When we use a lexicon containing only one entry for each pinyin, the performance is the lowest. When we use all the possible pronunciations we can observe from the database, the accuracy is improved. But when we reduce the size of the whole lexicon, and the final result is still is better than we use the full set of the lexicon. So we think when we use multiple entries, it will cover most of the yes. I mean if we use too many entries for each pinyin in the lexicon, it will introduce some unnecessary confusions between the sound changes. So, but if we use only one entry for one pinyin, it will not cover the necessary pronunciation varieties. So we should use a moderate sized lexicon here. Okay. So much for my talk.
Just to conclude this group of work on modeling GIF acoustic models, we have, from our experiments, we have seen that GIFs give better performance than IFs on the cast data. And we want to investigate, actually on perhaps with more database in the future, the actual phone and sound changes in Mandarin casual speech and with accents. And the next thing we're going to do now is to cross-domain, to apply the methods we have experimented on cast data to broadcast news and call home databases, including which includes these 4 different kinds of approaches from our group. Next, I will turn over to Terri to talk about her work on predictive features for pronunciation modeling.
Summer, it was suggested that I try to look at measuring the sound change that was annotated in the CAST database and try to just predict, like measure it from the waveform. So the first thing I did was take a look at the counts. And this was the first table I came up with. With the voiced, unvoiced, it seemed like the only one that had enough to do any development on. There are other sound changes in the database, but it's not clear how to get to them. And this particular table is a list where the linguist explicitly put a character that was easy to parse. So this isn't necessarily the total picture about sound change, but this is where we started at the beginning of the workshop. So we went to the waveform and tried to predict voicing. This was very appealing because Entropics has a tool that will measure it for you, so I didn't really have to do any work to turn it on. In this particular case, this line here shows their voicing decision. They make a hard decision, so it's either 0 or 1, frame by frame. And we can see that it indeed is finding voice sections pretty well there. In this particular example, there's this voice T that the algorithm didn't agree was voiced, and this is also a final that should be voiced. The algorithm didn't pick that up either. So I took a look at how well the algorithm correlated with what the linguist thought truth was. And this is a DET curve, a detection error trade-off, which just shows the false alarms versus the misses. And we get about 20% false alarm, 20% miss, and we consider that to be high correlation with the linguist. So to bring it into the process, I took an alignment that would come from Umar's tool. This is the reference canonical form. This is what the linguist would have transcribed. We took the reference form and did a forced alignment with some initial models that Bill had to get a start, like a start and an end point, so that I could make a voicing decision over a segment of time. And then this just shows for whatever start and end time for that phone or for that initial final, what portion of it was voiced. And in particular, this should be a voiced final, but the algorithm decided it was really not that voiced. Presenting these as probabilities of voiced, allows us to explore different thresholds. Unfortunately, we didn't have time to do that during the workshop, so we just picked 0.5. If this number was above 0.5, it was voiced. If below, it was unvoiced.
Excuse me, I'm a little uncertain here. So, is one of the columns the canonical pronunciation, and the other one
The first
the
column
way
is
this
the-
Cass transcribed it?
Right. This is the canonical form, and this is the way Cass transcribed it.
Including that something that in canonical was, say, unvoiced becomes voiced.
In canonical, there weren't any voiced, unvoiced.
No, I didn't mean that. Oh, I see. I'm
Well,
sorry.
you
In the
assume-
canonical, there is no distinction between voiced and
Well, in canonical, you assume that the vowels are voiced and the nasals are voiced and the rest is unvoiced. And you can make assumptions like that. And then in Cass, the linguist noted exceptions for voiced and unvoiced. This is actually a stripped down representation of Cass, so
So
it
are
doesn't
you-
actually have the sound changes notated.
So if they say something is voiced, and you then look at the waveform,
Yeah,
you sometimes find that they were wrong.
Right.
Is that
correct,
right?
correct. Well, they were wrong from the algorithm's perspective. I don't know.
No, I understand. They heard it voiced, but your signal analysis,
Right, preferred it to be
however accurate
unvoiced.
it is, said it was not voiced.
Right, right.
Yes.
Can I ask another question?
Yeah.
When you said that you did a forced alignment using the reference transcriptions, the IA example that you gave,
Right.
whatever frames it aligned with, in that region your voicing detector said there's only a 0.15 fraction that is marked as voice.
Right.
In the hypothesis column, there are some time marks, right, in the Cass transcription.
Right.
If you took those as your alignment, do you have a feel for whether those numbers change?
Well, let's see if I can go back.
As in, my basic question is, do you trust your alignment?
This curve was developed based on the linguist's time marks.
Right.
From it, I feel as though, we can trust what the algorithm's doing regardless of where the time marks start and end. And I don't know that there's a way to actually measure. So, we're going to do a forced alignment with canonical pronunciations on models that aren't really that good yet. They're just initial, flat start kind of models. So, can you trust your time marks? I don't know. Maybe they're good enough, maybe they aren't. But you got to start somewhere.
Yeah, my question was, I'm still not sure what you're going to do with this three-column alignment, but wouldn't it be better to use the alignments based on the second column, because there's at least, that's the one for which you established a good relation.
Well, if you use the alignments based on the second column, then you can only really do it in Cass. So there's no way to apply it to broadcast news or to call home, or any future, less annotated database. So, that's the ideal situation would be to use the actual linguist marks, but it's not realistic. So once we have this voicing decision associated with an initial final, we can feed that information into decision trees and use it in trifone clustering, and Veera and Bill will talk more about that. They'll also give more detailed performance than I'm giving. The initial experiments indicate that voicing is useful to predict some pronunciation change. And in the future, we hope to look for more features and build acoustic models that are actually sensitive to the features that we can measure in the waveform.
Okay, so I'm going to... I'm going to talk about our attempts to apply some of the pronunciation modeling techniques that have been developed here and elsewhere for English to pronunciation models trained on the CAST database. This machine? Okay. So referring to previous experience in English, the pronunciation models that we mostly did in English, there was a project here in 1996, and then in 1997, the 1997 model project for English conversational speech used annotation of the switchboard corpus. Here's examples here. The base form, the dictionary pronunciations of just because they're grandparents has this form like this. The surface form here, an alternative pronunciation. It's closer to what the person actually says. Instead of saying just because, they said just because. I can't mimic it. Grandparents. But the point is, when we first got the data from the transcribers at Dixie, the first thing we did was stripped out all the diacritics because we didn't know what to do with them. And there was still plenty of sound change. Now, the problem is, when we did this for CAS, we stripped out all the diacritics and there was no more sound change. And so, we sort of found ourselves in a bind. So we're sort of trying to, sort of modify the CAS, work with the CAS a little bit, and also expand the pronunciation.
Excuse me, when you say there was no more sound change, that means that all the sound change was in diacritics.
Yeah.
Is that right?
Yes. That's not quite true.
So
but
L never changed into M or anything like
that? A lot, an awful lot, to the point where we didn't even bother to try to build models to predict it. Okay, so we're taking two approaches to deal with this simultaneously. We're going to try to extend our modeling methods to capture sound changes, and if we're having some success with this, so I think we'll return to the ICSI data and attempt to do it there as well, to try to use the diacritic information that we ignored previously. And just as an aside, as Terri mentioned, voicing was the easiest one to start with, the easiest one to measure, and so that's what we started with the idea that if we can't incorporate voicing measurements, we won't be able to incorporate anything. And the other thing is, the attitude, at least I've been taking, I don't know if all my colleagues share this, is that you pretty much take what you get when you ask somebody who understands language very well, when you ask them to transcribe it. You might have something in mind that you would like from them, if you're going to build a speech recognizer, but probably that's not exactly what you'll get. So you take what you get and you try to work with it. So what we're going to try to do is attempt to derive phone change patterns from the CAS data itself. In other words, try and figure out if we can get what we would like from the data even though it wasn't provided directly. So here at this point, Veera talks.
Okay, so I'm going to give the details of how we actually went about changing the methods of pronunciation modeling. We would like to have additional information to model the sound changes. So what you're going to do is, for each and every diacritic that that's present in the CAS corpus, we would like to incorporate gradually one by one into the pronunciation modeling methods and see if it works. And as Bill said, that we started off with voicing, and voicing can be measured directly from the acoustics. That was what Terri was talking about. So we do a force alignment between the base forms and the acoustic data, and the pitch tracker gives a tag to each base form saying whether it was voiced or unvoiced, and then we use this information to predict surface form phone changes. So I'll just give an example of a decision tree pronunciation model and then say how voicing helped. Okay, so this is a slide to illustrate how pronunciation models are built and also how they can be used. So this is the base form string, and we would have built trees for each of these base forms depending on the context. And for each of these base forms, we will apply the tree in the context, and it's going to give out the most likely realization of that base form. So for example, this EN in this context the pronunciation model says was most likely to be realized as N, then En, and could also be deleted, and so on. Okay. So when we add the voicing tag to the decision tree building process, this is an example, a very good example of what happened. So this is a decision tree for the initial SH. There were 3,720 occurrences of this base form, and 2,823 times it was realized as itself. Okay, and to the decision tree building process, we filled a bunch of questions. One of them is check if this phone had a voicing tag of yes or no, and the decision tree decided that the best question that we could ask is the voicing detector's output, and it decided when it is indeed voiced, then it actually when it is voiced, then it's most likely to be an SH than an SH.
Excuse me, this voicing tag is in the lexicon.
No, it comes from a direct measurement of the acoustic data. So the the base form transcription is tagged with the result of the voicing tag.
What is being measured?
Okay, so we take an initial, so this is during training, so we take a forced alignment with a set of models. This gives us a time segmentation for every utterance in terms of initials and finals. Terri runs the voicing detector over that and labels each initial and final, whether it's voiced or unvoiced, with respect to the probability of voicing at a threshold of a
The voicing decision is a temporal decision for the sound.
That's right.
Yeah.
So it's based over the entire frame, the entire alignment, a
What's the
particular
criteria? Because in English, for example, if 1/3 of the duration was voiced, you would probably consider it voiced. It's arbitrary, not arbitrary, but it's not quite correct. What's your criteria?
Well, Terri?
Well, we initially just looked at it, if at least half of it was voiced and not just voiced. That's the starting point. We didn't really explore all the grammar things.
I am not sure now. Now, during training, because you have a forced alignment, you know when it begins and you know when it ends.
That's right. So
Then you run the detector for this interval and decide whether it's voiced or not voiced.
Right.
So now you have training data which is annotated.
Right.
So now, and the way I see it there, that if it's voiced, then somebody says it's a je. Who says it's a je?
The surface form. This represents the surface form.
I see. So,
this is in the cast transcription.
yes. So in the canonical thing, it was SH, and in the
surface form.
No. And in the sound interval, it was voiced, and then you predict that under such circumstances, the cast transcription will be je.
Right.
Right. And now, how do we use it during recognition?
So this is only being used to predict phone change at the moment. So we're using additional measurements. So we're staying within the canonical model set.
No, but for this answer, yes, you would need a time alignment, right?
Yeah, to get the voicing detector output.
Let's just, at the moment, we're just trying to build decision trees to better predict the cast transcriptions. Let's leave it at that for the moment.
Okay.
And do we care what the adjacent sounds are?
Sure, those are questions that are also considered in the tree. This is a simple example that where the only question was whether is this phone voice, is the sound voice. But in other trees, it's more complicated. The voicing question is mixed in with other questions about the context.
All right.
Okay, so I gave you the details of how we changed the modeling methods. Now I'll talk about how we reasonably changed the corpus so that we can derive phone changes in the corpus. So CAS,
Still on training corpus.
this is still the training corpus.
Okay.
So the CAS corpus does not have extensive reduction marks. What I mean by that is the time refinement is very high. For example, they have marked phones whose duration is less than 10 milliseconds, sometimes they're even 5 milliseconds long. And our modeling methods require phones to be at least 30 milliseconds long if we can model it properly. So Terri ran a small experiment and dropped phones which were less than 10 milliseconds, 20, 30, and those were the percentages of the phones dropped. So we decided to drop phones that were less than 20 milliseconds, and we carried on with that. CAS uses diacritics extensively.
That means you give up on annotation.
No, we say that the phone was not said at all.
Was not?
Was not said. Was not spoken.
You take it out of the transcription.
Okay.
So CAS uses diacritics extensively. We've spoken about that. Voicing is the most frequent diacritic, and so what we did was we mapped phones for which we have a counterpart into that one. So a voiced P in English is usually a B, so we map it into that one. We are not sure about how justifiable this is, but we just wanted to see if this was going to help the pronunciation model. Okay. And ideally, this artificial variability will allow the acoustic models to find this consistent variability, this consistent phone change. Okay, so this is an example of an artificial phone change. So you can see out here, this T_V, this voice T, was less than 10 milliseconds long. So we would have dropped that, and once again there's one more initial. This Z retroflexed. This would have also been dropped.
But just before you go, you can look at the waveform and see why it was so hard for the transcribers to annotate. It's very noisy.
So what's your point here with this slide?
The point is that we went through and arbitrarily picked a time threshold and dropped things. And one of the things, probably the retroflex Z, maybe that should have been dropped. But the stop, maybe we shouldn't have dropped. But the point is, we're just throwing them out, and then because of the modeling process that's coming in next, will allow the models to rehypothesize them if they prefer.
All right.
Yes, Jay?
Just so I can understand the examples, could you explain, just in one sentence, the difference between what is transcribed as P_V and what is transcribed B, P_V and D, just very quickly.
Pascale, do you want to?
What was the question? P_V and P.
P_V and B, different.
They're actually different. In Mandarin, that was the assumption they made. That's possibly more true for English than for Chinese. P_V in English maps to B, but in Mandarin, the B is actually unvoiced.
No, I think what in English what they would map to is an initial B with no sound before it or a voiceless sound before it, and a B preceded by a voiced sound. In other words, pre-voiced B and unaspirated non-pre-voiced B. That's what I'm trying to get at, whether these are simply common allophones of phonemes, and why aren't we using those words? Is there something more here than when I hear T_V and only a few milliseconds assigned to it, it doesn't make any sense at all in a language that doesn't have T. It has varieties of D with various amounts of pre-voicing, but I guess I thought I was missing something.
We should show you the sample table later, but these sounds are, these symbols are.
They're sample, not the IPA.
What did you say?
The T_V I think is D when you convert it to IPA.
That's not the point. I
Oh.
get
Correct.
the point. You're talking about that you should use a different set of sample symbol.
No, I'm trying to recover from what I'm hearing, the difference between contextual sound differences, such as, let's say in English, a free voice B, which occurs when the previous sound has a vowel and so forth, which are predictable, or to a certain extent predictable allophones, from other types of variation which are not predictable from the context. And because I'm not familiar with the terms sound change and phone change being used the way they are, I'm having a little trouble following how these models are being built and what context is being built from. That's the point of my question.
These are not. Well, the B sound in Chinese, it's really just on voice B, and I don't.
But I'll bet you when it's preceded by a vowel in fluent speech that it's free voice.
In Mandarin.
Yes.
When it's preceded by.
Preceded by a vowel in fluent speech.
Voice vowel.
Yes.
I don't think we're studying this here.
Yeah,
This is,
okay, I think I understand the distinction.
So,
So it would be free voice if it's preceded by another vowel in
Yes.
the previous word, yes. Okay, all right.
what was that?
Go ahead.
She agreed with you.
Okay, we'll continue. Okay, so this is an example of a cross-domain application. We built the trees for CAS, and then we wanted to apply this tree on broadcast news data. So we have the CAS transcriptions out here. With those CAS phone transcriptions, we come up with the CAS tree pronunciation models. We feed in the base form broadcast news transcriptions and come up with broadcast news lattices, initial final lattices. We then use HMM models through the lattices and come up with a surface form transcription of broadcast news. And out here we feed in this block into here and come up with a base form to surface form alignment.
Excuse me, I don't understand it at all. When we talk about lattices, aren't we talking about recognition?
No.
No,
No, we're
okay,
talking-
so what are these lattices?
Okay, so these lattices are derived by taking the base form transcriptions of the broadcast news and applying to them the trees that were learned from CAS. So the trees represent a large range of changes that could come from any set of base forms, and those changes are represented in a lattice.
So in the tree that you gave an example of, there is a distribution on the leaves, right?
Yeah.
And that means that that's where the lattice comes from, because there's a distribution and you give some branch to each
Yes.
element in the distribution that has, quote, positive probability.
That's right, yeah.
Right. So there is no recognition here at all in what we're discussing.
No.
Is that right?
Right.
And we're, excuse me, just want to understand it. And we're dealing with still training data.
Right.
So we're just dealing with how to create more detailed training data. I mean,
Yes, yeah, you can think of it that way. So but to get to your question from earlier, what do we do with the voicing tags? They're only used on these first steps in the lab.
yes.
So we use them as part of the voicing information is needed by the decision tree when it generates the alternatives. But the alternatives don't contain voicing tags. So at the moment we're sort of moving towards incorporating features into the pronunciation model. And we're just using them as a feature that's used to predict these alternative forms.
Okay.
You want to continue?
Yeah, okay. Okay, so these procedures that we're using, we're grateful to previous work by Murat Sarıklar for working out a lot of these procedures, and also from the AT&T group. So what we do is as I just said, we generate these alternative pronunciations that are in lattice form. We take an existing set of broadcast news hidden Markov models and do an alignment, and this gives us and that chooses among these surface forms. So then we use this gives us for every base form transcription an alternative surface form transcription. So for the first set, the first product of this procedure that we can use in recognition is found by applying a word dictionary to these alignments. So this will then tell us for every word, based on the alignments, what are the frequent surface form pronunciations. And we can count the number of times each word has a surface form. If we can count each surface form alternative for each word, and this gives us a weighted dictionary for broadcast news. Okay, we can also then take the broadcast news base form to surface form alignment and use it to retrain trees. This was found to be useful in the English in the conversational speech using ICSI data. So then we repeat the process again. Retrain trees, generate lattices, realign the lattices with broadcast news HMMs, and then the next step is we want to. In the previous step, we got a dictionary. The next step is we would like to retrain acoustic models. So the alignment using Umar's tool that I forgot to mention in the previous step, we can align the state level triphone. We can align the triphones at the state level, and this will tell us how to share Gaussians to construct models to construct new models, essentially to take the original base form Gaussians and add mixtures to them based on the surface forms that frequently align with each base form at the state level. And this in the bottom box will give us a new set of HMMs, and then we can also continue to do an alignment and get a new dictionary. So, wrong machine. Okay, so here's the obligatory unreadable slide. We evaluated this on Mandarin broadcast news, so we used the acoustic models for HTK 12 mixture state clustered. I keep wanting to say triphones, but they're really context-dependent initial final models. They're with cross-boundary context-dependent initial finals. They're about 2,000 states. The training set was 10 hours of standard Mandarin Hub4 training data. So this was from the LDC distribution. It was reviewed by Liu Yi to make sure that the speech agreed with the transcription, and also that the speakers that were selected were, spoke Mandarin well, because we're interested primarily in Mandarin here. For decoding, the dictionary was 50,000 word and character Topinion dictionary that was provided by Thomas. And the character bigram language model used 20 years of the People's Daily plus the text resources that come from LDC. For the test set, we used the clean, the F0 utterances from 1997 and 1998 Hub4 test sets. This came to about 1,263 utterances. So the baseline performance, which is just the regular, this is reported at the character error rate. So the decoder is running with the words with a word character dictionary, so it generates words and characters. You break the words up into characters and you measure the character accuracy. Okay, or the character error rate. So the baseline is 28.6, 28.7. In the first step, I should have turned this on earlier. Does anyone know how to turn this on? Okay. So in the first step, using the baseline HMMs, and the dictionary that comes from aligning through the trees, we get a reduction of 0.4%. And then when using the baseline dictionary, but with HMMs that come from state sharing, from triphone state sharing, we get a reduction with respect to the baseline of 8%. And when we combine these two methods, we get a reduction of 1%. So these new dictionaries and the acoustic models, they seem to be effective. I should say very little tuning was done. As Pascale mentioned, we really just got down to work about 10 days ago, and this pretty much came together over the weekend. The techniques need to be refined. In particular, I think they'll benefit from a larger and more varied acoustic training set. As you can see in this slide, the purpose of the way you can think about the training procedure is that you generate these trees, and they generate all this huge number of alternatives, and then you use your existing HMMs to refine the number of alternatives for each word. If you have a training set that's relatively, and so the refinement is based on the variability that actually, it's okay, I can do with that. The refinement is based on the variability that's in the training set. and as I told you just a minute ago, the training set was chosen to have relatively good speech. So I think we'll find, as we move to a larger training set, and hopefully even to the call home data, that we'll find more variability. And to summarize, the CAS data is useful. We found that you can train pronunciation models on CAS, which is this sort of, I don't know, public meeting domain, and apply them to broadcast news. And also, I think, which is, I think new, maybe not new, is that we can take direct measurements as acoustic side information and incorporate them to predict sound change information. Sound change. Okay. So we're inching towards GIFs, and the problem is not a problem. As everyone has spoken before, the GIF dictionary is very rich in pronunciation alternatives, and it's difficult to decide which of the alternatives to use. We want to choose the GIF pronunciations based on pronunciation models, so we have these trees that predict which ones to use, and we would like to also include into the choice direct acoustic measurements. So, for instance, we choose a GIF with a voicing tag if the voicing measurements say we should. Okay, and so we've talked about voicing because it was the easiest to get at in a short time, but we're also interested in other measurement techniques. As alternatives to explicit GIF models, I think this has been mentioned before. We're really interested. A GIF model will be what's the probability of some acoustics given a particular initial, and knowing that it's voiced. Well, we would actually want to derive this from the probability for the initial given any B, whether or not there's this additional voicing information. This is not derived from the dictionary. This comes from some side measurements. The point is that it's not possible to train models for all these variables. So one thing that I started working on was incorporating this information into triphone clustering using methods that were started by the 1996 hidden mode group. This is not quite the same thing as a hidden mode, but the modeling techniques are the same, or can at least be applied. So the way the application would work is like this. So you label the entire acoustic training data with voicing tags, and then you ask questions about the voicing information inside triphone clustering. And the nice thing about this is you can incorporate into the cluster, you can extend this to include additional features if you can measure them. And we started doing this, and they're actually chosen. Here's examples. These came from the real training data on using trees that get to ask questions about what the voicing detector says. So here's the first and second states of the initial G, and in the second one in particular, the first question is asking about itself. Is its own voicing? Is it unvoiced? And then it asks questions about its neighbors. And similarly, the second one, it asks in the first state of the phone, it gets the second question is it voiced or not? So we're hoping that actually have the decoding is something of a challenge, but we have it set up to run. So hopefully we'll get back to that after in the work immediately after the workshop. So I think that ends our presentation. Before the break, how are we for time?
Fine.
Fine. Okay. So.
So we'll have a half-hour break.
Yeah.
And I have a question.
Okay.
So this whole business that you went into before, that means the trees, and the decision trees, and the voicing decisions, etc. The purpose was to enlarge the base form dictionary, really. Where the original base form dictionary has essentially one pronunciation per what? Character or per word?
Per word.
Per word, and now we are going to have multiple.
Yes.
And you have some threshold on it, etc.
Yeah.
And then the acoustic models, I assume, are then trained with, relative to the enlarged dictionary?
So the acoustic models, we use the base form ones, and the only retraining we've looked at so far is state sharing, which comes from an alignment through the pronunciation lattices.
So the alternate base form, I don't know what you want to call it, alternate forms are not used in training of the acoustic model.
No, they are. They're used. Yes. They go in as alternatives. So how do you go backwards? So here, suppose this is the first state of the initial G. Suppose that often through the pronunciation alternatives, it turns out that the first state of B is aligned too. Is aligned often with this one.
I'm sorry, I'm not, I thought we have now, that we have words, and now we have several base forms.
Yeah. No. No, we have a word transducer and we have a word transcription. Okay, so we have a canonical initial final transcription that's derived from a word transcription. Okay.
We're now talking about, we have character strings, right?
Yeah.
All right. Those we have segmented into words,
Yeah.
into word strings.
Uh-huh.
To each word there corresponds K different base forms.
So let's say one to keep it easy.
Well, if it's one, then well, if it's one, then it's one. But why did we get the alternate pronunciations?
For two reasons. We want to build up the dictionary to allow more pronunciations.
You allow more, but you don't use them.
I do use them.
You just said that there's only one.
I'm not sure. Well, in which context? I don't know. We may have gotten confused. I said, say in the canonical dictionary, there's one pronunciation.
Yes, and then I thought your methods got us alternatives.
That's right.
Now, how are we using the alternatives?
So we're using them in two ways. We're using them with the baseline models. We're just adding them to the dictionary. That's one way. The second
Where
way.
the HMMs were trained without them.
That's right. The HMMs were trained from the baseline dictionary.
Right.
And the
Okay.
second, yeah.
So there's one way.
The second way is to determine what states are aligned, what states in the surface form align with what states in the base form. At the for triphones.
Yes.
And then we borrow Gaussians from the surface form to add to the base form.
All right.
And so that uses the baseline dictionary, and then we combine the two.
So for the different surface forms corresponding to a single base form, where you don't have correspondence to actually borrow, or you can't do state level time, what do you use?
No, we have
So you copy all the states and the Gaussians for all the states.
No, we keep the Gaussians from all the states. The way to think about it is you keep them and you go and borrow from their neighbors
Right.
based on these alignments. So you never lose any states, and you keep the same. The names of the states stay the same. You want to think about it in practical terms. You're just adding more mixtures. This is another way to think about this is you're going back and fixing the clustering. Clustering was bad the first time.
So you would expect to actually, this is just an initial model. You retrain that, you would expect to improve.
Oh yeah, I left that out. I mean, there's a couple of iterations of Baumol's training after this stage. Yeah.
When you open the dictionary, you don't use the decision tree to actually expand your pronunciations while doing the decoding?
No, we took the easier approach of building an enlarged dictionary. Just enlarging the dictionary and then using the dictionary. You could do what you said as well. This was easy.
Did you find problems with the voicing?
No. So the voicing information is just used to predict.
Yeah, so if you were going to use the trees on the fly, then you would find a problem because.
Yeah, good point. Yeah. Did everyone follow that? I mean, the problem is if we wanted to incorporate the trees directly into the decoder, we would have to make on-the-fly voicing decisions, so we would know, what tree what decisions to make in the tree.
But it's like the capstone computation. You always compute the capstone beforehand, separating and computerize the time.
Yeah, well, what I actually did was I generated a lattice initially with time alignments, and then just taking those time alignments, I went back and recomputed the voicing tags, retagged the entire lattice, and that's what we'll test next week.
If you have these alternate models, one with voicing and without voicing, just put those models in parallel.
Oh, but I don't have that. And I don't think I necessarily do want that. I mean, I don't want to carve up the data that way. I want to use the voicing information to help predict the changes. I don't want it to say, okay, I've got voice models and I've got unvoiced models.
That's actually more similar to something we do with the probabilistic lexicon, right? We work directly from the models.
Okay. questions about substance are delayed to 4 o'clock. That's that. Go ahead. So we're about to start.
There's actually 2 on switches.
On. Okay. Okay, welcome everyone to the end of the presentation. We just finished. This is a discussion session, and I'll quickly run through the important points of our work. The first important point is that everything worked. Everything we tried worked with respect to the baseline. This is not saying much, but it's saying a lot for us because.
By baseline, you mean the broadcast news?
The CAS and broadcast news, both. Right. So we can continue to apply these methods with different databases and so on and so forth. We also found that from different experiments that GIF is better than IF on CAS, even when data is sparse. So maybe that's idea. The idea we draw from that is we can use GIF transcriptions to bootstrap. Okay, words are good, better than syllables. Actually, in other words, we want to say is context is important. So there are more sound changes also than phone changes CAS Mandarin. We suspect that these are more transcription artifacts because of the linguists, their own convention, rather than the reality. Meaning that when we listen to the corpus, okay, it seems like the linguists hear things we don't hear. So another point I want to make is in response to Jack's earlier comment. I think I used a bad example earlier when we have the 一点人 becomes 一点人. I want to clarify the point, the following point, which is that the 一点, the R comes after 点. It's not because the following character starts with an R. That was an unfortunate coincidence. In other words, I can very well just say 一点 without 一点人, 一点门, I can just say 一点. So these sound changes are not lexical. They're not because of the context of the characters, but they're rather, they happen because of casual speech style, casual speech speed, so on and so forth. We have, Umar has successfully developed flexible alignment tools we're all happy to use, we've all used it, and we hope that others will use it as well. We can use state-level Gaussian sharing. We have used that for IF in both Liu Yi's and Bill and Veera's experiments. And we want to find out when we go home that whether we can do that between GIFs and IFs to enrich the Fungian models. We have developed probabilistic GIF lexicon. This is again something that it is important to use alternative forms, but well, it's good to use alternative forms, but it's only good to use these alternative forms if you have probabilities associated with it. Otherwise, you're just getting more confused. Your recognizer will get more confused. We can use bootstrapping with a small annotated corpus of GIFs. So another point we have discovered is that using adaptation sort of from GIF to IF and from IF to GIF, becoming S GIFs and big B GIFs. Again, to support our argument that context is important, context-dependent equivalent classes have proved to be very, very useful, especially when data is sparse. We think that that's also useful even if there is an abundance of data. Again, these contexts we believe not to be lexical, but occurs in casual speech. Syllable engrams, we use broadcast news syllable engrams, and we use people-stated syllable engrams, and we apply that to CAS and worked fine. So syllable engrams are useful across domain. Terri has found that there's a high correlation between automatic voice sing prediction and the linguistic transcription. So we believe that the linguists did a good job when they transcribed voice in future. I don't know about the other things. Direct acoustic, this is very important. We can use direct acoustic feature without a pronunciation dictionary. And we have an established framework for incorporating such direct measures into a pronunciation model. And we also have used acoustically sensitive state clustering. According to Bill and Veera's work, it seems like methods that work on conversational English can also work on CAS with suitable modifications. We have developed reasonable ways to derive phonetic variability from the corpus. I should point out that phonetic variability here is different from the sound changes, which is defined by diacritics, which is described by diacritics. Word pronunciations must be inferred directly rather than from syllable pronunciation changes. So you can, again, this is part of the argument that words are important, context is important. You don't want to just concatenate variable syllables to give you word changes. In other words, if you have a word, to derive its alternative form, you don't want to just do a bottom-up, concatenating different kind of syllable changes into a lattice, and you don't want to do that. You want to use word. And we've done cross-domain pronunciation modeling by successfully applying the features discovered from CAS database to broadcast news database. So these are the important points. We'll open for discussion and questions. Yes?
You're ignoring tone. Are there any experiments that show that that's not important, tone?
It's not that tone is not important. In fact, in I should also point out, again, emphasize that our work was focused on standard Mandarin casual speech, meaning nobody had a strong regional accent. Tone information, tone changes is one of the most important changes in accented speech. We do believe that it's important, but we don't have, so far, the state-of-the-art technology cannot give us really good tone recognition. So perhaps in our other ongoing work, when we work with accented data, we can try to do something with tones. But the recognition rate for tone is usually very low and gives you, usually Mandarin recognizer works, has lower accuracy when there's tone information explicitly, when you use tone information explicitly, because the information is off. So we think it is important. It's very important, but we don't know how to recognize it correctly and accurately enough in order to use it.
Tone and tone sending are actually marked though, aren't they, in the data?
Tones only, the actual tones, they are marked, but we didn't use them.
As realized, not as lexically.
Both.
Both.
Both. Yeah, both. Yes.
I didn't quite understand what your baseline was. I have two questions. First one was, were the baselines also context-dependent initial finals or context-independent?
No, context independent. Them is strict baseline, initial finals, and context independent gifts generally.
What kind of language model did you use?
I'm sorry?
What kind of language model did you use in baseline?
When we test the syllable accuracy for our test, we only use the syllable engram. We test it, we value on the CAS database, but we use the syllable engram from our database.
The broadcast news
From broadcast news.
had a regular, normal word by game.
Do you have a question?
I was going to ask you about the tones.
Same
We hadn't heard about that.
Well, let me ask you, tell me again, what does concretely the generalized mean? In other words, what is the additional refinement that we get from initial final?
Okay. For example, in this example, okay, TS, okay, it's a canonical initial. You know, we have a canonical initial and final set defined by the dictionary, bilinguals, everyone uses that, right? And there are sound changes, so TS underscore V and TS, you know, quote at least. These are not in the canonical set.
I see.
So we include that in the generalized initial final set. The problem with that
and this is standard, or is it yours?
This is Sampa. This is the linguist convention. Their notation.
And so this comes from Lily?
Yes. Yes.
Right. So the initial final is universal.
Acknowledged. Or
Chinese.
Mandarin.
Oh, Mandarin.
Dictionary.
Dictionary. And then she added some additional elements.
Yes.
Right.
So the
GIS
problem
are
with
actually less general.
sorry?
The GIS are actually less general than the IS.
No, it includes the IFs. It's it's a bigger set than the IFs. It includes the
They are more
IFs.
specific.
Yeah, more specific.
They are context, in some cases, context.
Oh, instead of saying generalized, it should be specific.
And why do we have these Z's on the left-hand side? In other words,
Oh, this is Z's are the written pinyin form. Z is how we write the pinyin. And then TS,
and you pronounce it
TS, that's the IPA.
Oh, that's the IPA.
Yeah. Sampa. Sampa.
That's the sampa.
Which is good.
So why is it?
Because
why is it Z in?
That's a Romanized Chinese
I
pinyin
see.
standard.
There must be some historical reason for that, right?
This is the pinyin convention. Before that, there was Wei Zhao's that uses TS in this case.
I see.
But that's a pinyin
It may come
pinyin
from
set.
It may come from a
Alphabet.
tradition in which they tried to avoid using digraphs. There used to be
Right.
an inclination to do romanization without using digraphs.
I see.
And so the only character available for zi was C, like in European, some of the European languages. But then if Z is not used in the set, then Z was a common.
I see. Right.
Yeah, and ZH is the ritual flex equivalent of Z.
Now, can you tell us anything about the circumstances under which one can expect zi to be realized as ch? Or
It's not zhi actually here. You mean this case changed to zhi? You mean the third case?
can you give me any generalizations about when those four variants are used?
Generalization, no, it's not lexical. It's not because there's some it occurs in casual speech. We
They're
have
not random.
computed.
Surely they're not random.
Surely they're not. We have all these probabilities.
We can get it from the data.
Yeah, we can get it from the data. We have those.
So I'm asking, can the linguist tell me under what circumstances they use? Are they in fact allophones of zi?
No, the allophones, they're not allophones.
They're not allophones.
Do some people tend to use one more than the other?
Oh, in accents, yes, but this data is not. Accents, like all Southerners, pronounce all the ritual like zi and zi, zhi, chi, shi as zi, zi, zi. All the Shanghainese, Cantonese will say zi, zi, zi rather than zhi, chi, shi. Southerners don't have ritual flex, and the Northerners have a lot more ritual flex. In this case, but there are the sound changes that are not lexical. It will be interesting to study the set and see, generalized rules in an accented database. For example, for each region, what kind of changes are according to the context.
Is there something specially Chinese you're going to do?
Is there something especially Chinese?
In other words, essentially what Bill did is applied certain ideas that we developed here.
But they didn't work out of the box. So for instance, we had to change them to initials and finals. So a final can have several sounds, and it's more like the latter part of a syllable. So that's quite Chinese, I think. I'm surprised nobody's taking issue with our assertion that words are good for Chinese, because my initial approach was to do what people suggested, which was to work from syllables, and this actually was a very bad idea. It's not quite true that everything worked. Trying to infer word pronunciation from syllable variation is terrible. Some things I think are inherently Chinese and others are not. It's possible also that the voicing information is good for Chinese too, more than it would be for English.
This is a slide from Professor Lee's talk. Maybe Jackie were not here when the linguist gave her talk. These are basically some variability factors that the linguists think that cause some variabilities in Mandarin or in Chinese. Dialectic accent I mentioned before, we're not working with it this summer, but that's really a major factor. Prosodic structure, co-articulation context, that's what you were talking about. Here, this is an example where ZH systematically becomes Z without racial flags in southern accent. And there are other things for Chinese. For example, we don't know whether the tone changes will affect phone changes at all. We don't know. Since we're ignoring the tones. I think even when we go to accent, we're still going to continue ignore the tones because we don't know how to do it. But that's something, we never really put the tone together with the phones to study it together because we don't know how. But something, hopefully. This is there are some changes that are lexical. For example, the zhe and na, zhe, na, which means here and there. They are even in dictionary form. They have two pronunciations. 这个那儿那个这个那个这个那个. But other than that, it's not much lexical pronunciation change. Yes.
Can you say something more about this corpus? I understand it was done in classroom settings.
Oh, okay. This corpus was 3 hours of recordings of lectures and speeches that were, classrooms and amphitheaters. Yeah, different speakers.
The microphone was in a corner of the room.
Yeah, it's a recorder.
So why was it done that way?
Why was it done that way?
Yeah, as opposed to, you have enough problems without the additional problems of the microphone.
Yes. Yes. This was from the archive of the Tsinghua University radio station. We wanted to have standard Mandarin spoken casually, so we didn't have a lot of choice. Broadcast news has a lot of accent variabilities, and then there was not enough standard Mandarin, and there was not enough casual speech. This corpus turns out to be really, really casual. Like, it's a lot more spontaneous than we would like. And
but there's only one speaker.
No, there are okay. We can go back to the.
But at any one time, you're mostly hearing aids.
Oh yeah, at any one time is one speaker, giving a lecture, giving a presentation.
There's interviews as well. There was some material from interviews.
But there's no crosstalk.
No crosstalk.
No. So these are the speakers in the database we had. Were they 7 we used? 7. And these are these are their original dialect background, but these are people who lived in Beijing for more than 30 years or so they don't have much accent. Yeah, we try to separate the accent effect from the casual speech effect.
I was curious about the slide you showed earlier on the various factors affecting ramifications of casual speech. And with regards to the diacritics that your group considered in CAS that you did not use, how much of those belong to the various categories that you showed?
How many did you discard? We didn't discard any.
Oh.
You guys discarded.
Well, I don't think we can answer that. I mean, we don't, to answer that, we would need to know for every mark in the database, what caused it, you know, is it the way it should be, or is it influenced by one of these other factors? I don't know how we could get that information.
Yeah, I guess I'm not asking for
Yeah, she's
for
asking.
statistics per se,
Yeah.
but apparently, if the linguists who were working on the CAS database started out with this notion that here are the factors that affect, you know, what you perceive from casual speech, and then they come up with this diacritic marking. There should be some correspondences between the two, right? I wonder if you have.
You're wondering why there are so many voicing, seemingly like the other sound changes don't seem to be as significant as voicing.
No, that's not my question. What I'm saying is, there's a previous slide that you showed on the various factors.
Oh, you mean the linguist,
Yeah,
some variability.
So they started out marking that database with those factors in mind, and say, well, these are the factors that affect sound variability in casual speech. But then they went ahead and mocked casual speech with certain diacritics, and I wonder whether or not you noticed any correspondences in the way they.
The linguists mark the diacritics and everything else by looking at the spectrogram and by listening. So.
So there's no correspondence at all?
Yeah, I mean. Well, there were cases where they say, okay, this is, we hear that it's this sound change because of context. We think it should be this. In other words, they might have looked at, they have the a priori notion of what sound should change into what sound in what context. And these are exactly the data points where we disagree with them because we don't hear it, they hear it. So that certainly this kind of knowledge affects the way they transcribe. Certainly. This is not coming in from the recognizer's point of view. So even, I think there was one example where they even discovered that the actual data contradict very well held linguistic notion of sound change. They actually found that it's not so. That tells me that all their notions could be off. They actually found actual examples which contradict what they thought to be true linguistically. So when they mark it, they look at the spectrogram and listen.
So one measurement that the linguist made was to see if the speaking rate affected the variability, and that was inconclusive. That's right.
Oh, I'm sorry.
So we had variability per speaker and speaking rate
Yes,
per
yes, I
speaker.
remember
They
that.
didn't really
Right.
line up.
We did.
But it's also true that
She has more accent than anyone else.
but also that this is just over all the data together. We don't know how it goes in small regions.
If you went different patterns,
Yeah.
there might be
The slowest speaker actually has the most accent, so we don't know.
Well, thank you very much. See you all tomorrow and more.